So after the few examples of metric spaces, we are now ready to see the notion of convergence of sequences in a metric space. So let's define it in this definition. So let x comma d be a metric space. That means x is the set and d is a metric on x. And let's consider a sequence of points in x. Okay, so we just simply express that by saying that this is a sequence in x. Let me say a little about this notation. It's nothing new to us. We already understand the different parts of this notation because this is how we write sequence. We have always written sequences of real numbers. For example, we understand that this n is the index which we use to label the terms of the sequence, and it starts from the integer n. N may be negative, n is just any integer. Infinity indicates the fact that the terms go on and on without any end. However, so far we have only seen the label appearing as a suffix. Here it's appearing as a superscript. And to not confuse this with an exponent, we have also used brackets to enclose it. However, why superscript? Is it an arbitrary choice? No, it's not an arbitrary choice. There is a reason for it, which will become clear soon. But let's just move on. We would say that this sequence converges to that point x with respect to the metric d if this limit is equal to 0. So given that we have already reformulated convergence of sequences of real numbers like this in terms of the distance that we have in the set of real numbers, that absolute value distance. So it's understandable that this is how we should define convergence in a metric space, and that's what we did. Okay. And if you go a little deeper into the meaning of this limit, that is, if you get down to the level of epsilon and those things, obviously having this is equivalent to having this. That is, this sequence converges to x if for every epsilon greater than 0, there exists an integer capital N which is at least as large as that starting index m, such that the distance between xn and x is at most epsilon, less than or equal to epsilon, for all the index values n greater than or equal to n. Now the little argument you have to go through to see why this is the same as this, that I am leaving to you. Let us next see two remarks on this definition. Okay, next we have this remark. The remark first of all reminds us of lemma 12.1.1, which is where we reformulated the notion of convergence of sequences of real numbers entirely in terms of that metric we have on the set of real numbers, that absolute value metric, which in fact led to this general definition. So it first says that, and then it says that when d is understood, when it's understood what the underlying metric is, it's not necessary to every time write xn converges to x here. Xn converges to x with respect to d. That phrase with respect to d can be suppressed, and you can just simply write xn converges to x. Also, you can express that same thing by writing more casually this: xn tends to x as n approaches infinity. We have already done this when working with sequences of real numbers. In this next remark, we start by considering this superscript n in the notation for our sequence. We say that it's a dummy variable. That means we can change its name. Instead of calling it n, we can say call it k. That's not going to change the sequence. If you think about what a sequence really is, what is it? It's after all a function. For this type of sequence, it's a function whose domain is the set of all integers greater than or equal to m, and whose range is the set x, that x of our metric space. In that function, what is the role of this n index? That is the independent variable. So whether you call it n or k, that does not change the function, so that's what is happening here. And then this is also addressed that instead of writing n as superscript, you can continue to write n as subscript, but you will encounter a problem if you do so consistently. The problem arises from the fact that our xn's, the terms of the sequence, are no longer necessarily real numbers. They may be sequences themselves. That is where a problem occurs, and that's why this superscript has been chosen. It will become clear, okay, when it appears somewhere like that. One more thing, if you go back to the 6th chapter where we studied sequences of real numbers, there, do you remember, we solved 2 exercises which essentially showed us that it does not matter where we start a sequence. If you have a convergent sequence and you remove, say, a few terms from the beginning of the sequence, leaving the rest intact, then that subsequence also is convergent and converges to the same limit. That same thing happens here as well. If this is a sequence where, say, the index starts from m, some integer m, and it converges to some point x, then this sequence will also converge to x where m prime is at least m. If this m prime is, say, m plus 1, that means your new sequence has almost all the terms of the old sequence except the term xn. Even then, it will converge to x. So it is that thing which we have seen happens with sequences of real numbers. It happens in general for sequences in any metric space. And now we come to an actual example of a sequence in a concrete metric space, and we want to see where it converges or if it converges at all. So the step we consider is the plane, our R2. Okay. And the sequence xn, here n starts from 1, is defined like this. The nth term is this ordered pair of real numbers 1 over n, 1 over a. Now for this sequence, if we calculate this limit, where you can see that we are applying the Euclidean metric, L2 metric, to calculate the distance between xn and which point? The origin. Origin means 0, 0. So if you apply the definition of dl2, obviously it will be the square root of, you already know the definition. So ultimately it becomes square root of 2 divided by n, which really it converges to 0. So then by our definition, this sequence in R2 converges to 0, 0 with respect to the Euclidean metric dl2. Now if instead of dl2 we consider dl1, what will happen? Let's see. So if we change the Euclidean metric to the taxicab metric dl1, then the distance definition changes. So now the distance is this, and that turns out to be 2 divided by n, which again converges to 0. So in the taxicab metric also, with respect to the taxicab metric dl1, that same sequence converges to the same point 0, 0. Next, let us also see the sup norm metric dl infinity. Next, if you apply the dl infinity definition to calculate this distance, you get this supremum of the numerical differences, and this turns out to be the singleton set consisting of the number 1 divided by n. So that itself is the supremum, and I have already told you that in our present situation, this supremum is actually just maximum because we are dealing with finite sets. But anyway, so in this case it is 1 divided by n, so which again converges to 0. So in the metric dl infinity also, that same sequence converges to 0, 0. However, things change if we instead consider the discrete metric on R2, which we can. The discrete metric can be considered on any set. So next we consider the d-disc metric, the discrete metric. Now if you write what xn is, no matter what n is any positive integer. Is there any possibility for this ordered pair to be equal to this ordered pair? No. 1 over n, no matter how large n is always a positive real number. It is never equal to 0. You cannot put n equal to infinity because infinity is not a natural number. And as such, these two are distinct points in R2. So by the definition of discrete metric, the distance between them is 1. So the sequence of real numbers that you are looking at here, whose limit you are calculating, is the constant sequence 1, 1, 1, 1, 1 and so on. So it converges to 1, which is not equal to 0. So by definition, this sequence does not converge to 0, 0 with respect to the discrete metric. Whereas with respect to the other three metrics, L1, L2 and L infinity, the sequence converges and converges to the same point. So this raises the question of what the criteria are under which we can say that this sequence will converge with respect to the with respect to all these four metrics. So that comes in the next result. In the next result, we are about to see what the criteria are for convergence with respect to L1, L2 and L infinity. For the discrete metric also there is one criterion which we won't see today. Okay, so let's see the next result. So this is that result, proposition 12.1.18. Do you remember that in the very beginning when we started discussing metric spaces at that point, and in fact when discussing the examples, I mentioned that these metrics dl1, dl2 and dl infinity are in a sense equivalent to one another. So this is that equivalence. In fact, that's why it's called equivalence of these metrics. So let's see, we have the space Rn, or more strictly I should say the set Rn, because we haven't really said what metric we are assuming on it. In this set, we have a sequence, any sequence, okay, xk, where k varies from m to infinity. Now, because this is a sequence in Rn, each xk will be an n tuple, and as such, each xk will have n number of coordinates. So xk will look like this, where the individual coordinates, which are of course real numbers, are denoted like this. And this is why superscript was chosen, so that we have place for subscript, suffix. If instead you wrote k here, then also you could have written xk1, k2, but some people find it a little disturbing to write two suffixes, double suffix. So for them, you can write in whichever way you want, but this is how the author decided to write. So each xk looks like this, and then we are going to need one point also where this xk will converge. That point will be again a point in Rn, so which has these coordinates, and so that is x. Now the following four statements are equivalent. You do see three statements here because I ran out of space. I am going to write the fourth one next. And they are equivalent to one another. That means if any one of them is true, then so are the others. So you see that these three statements are just about convergence of this sequence to that x with respect to the metric dl2, dl1 and dl infinity. If it converges to x with respect to any one of these three, then it also converges to x with respect to the other two, which is what we saw in that example. That is why all of them were convergent with respect to L1, L2 and L infinity metric. However, there is a fourth condition also, which will let you tell instantly if all of these are really true. Okay, so let's see what that condition is. So this is that fourth condition. Instead of looking at the entire sequence xk of these n tuples, what you can do is that you can fix a j. Say you decide that you would only look at the first coordinates of all these xk's. All the first coordinates, say you have xm, that is an n tuple. It has a first coordinate. Then you have xm plus 1. Say you write that below this one. So that also has the first coordinate. Then next xm plus 2, xm plus 3. All these first coordinates you can collect. That will give you a sequence, ordinary sequence of real numbers. That sequence converges to the first coordinate of your limit x, that other n tuple. If this continues to happen to all the coordinates, then and only then all these things happen. So if we go back to our example and test this fact there, what shall we see? Let's see. Say we go back to our example, okay. What was it? Our sequence was this, no? xn, where xn was this, right? So if you write this like how I said just now, it will look like this. x1 will be 1, 1, x2 will be 1 over 2, 1 over 2, and so on. And what was our point to which this sequence converged with respect to the 3 matrix? 0, 0. So if you fix j equal to 1, then you are actually getting this sequence, which is the sequence of the first coordinates. And that sequence is the ordinary sequence of real numbers 1 divided by n. 1, 1 over 2, 1 over 3, and so on. And we already know that that really converges to 0. If you fix j equal to 2, you get, in this case, exactly the same sequence. In general, it won't be, of course. So because both these sequences of real numbers converge to 0 and 0, that is why by this result, this sequence in R2 will converge to 0, 0 with respect to all the 3 matrices simultaneously. Okay, so as far as these 3 matrices are concerned on our space Rn, regardless of what n is, we just have to see whether the individual coordinates converge to some things, and those things then can be collected to make the n tuple. That will be the limit of your original sequence of vectors, original sequence of n tuples with respect to all these 3 matrices. So when you see these 3 matrices now, you need not even worry about the definitions involving square root, supremum. You just look at this and decide instantly whether it will be convergent. Okay, so this is really the heart of this result. And its proof we will find as an exercise, so we will solve it there itself. And let me just end the video here itself. And tomorrow, as usual, we have our upload. I forgot what we have tomorrow. I think it's either number theory or differential equations, because we have done differential equations recently. So tomorrow we will do number theory. So with that, let me just sign off. See you tomorrow with number theory. Until then, this is me, Lucifer from Mathematical Room. Have a nice day.